Happy New Year. We're going to do a little review and then do something a little bit new. So first of all, these angles coming out of the middle from the center, if the center is the vertex, this is called a central angle because it's from the center. It's got a good name. And one of the things we learned in class is if I've got a circle where everything's are spaced out evenly, it's easy enough for me to find out what the central angle is because I know there's 360 in the circle. So 360, in this case, this is 1/8 of that, just divided by 8. And so that's going to be 45 degrees. So I can figure out that. If I turn this into a triangle, one of the things people noticed in class is, oh, that's got to be an isosceles triangle, which means those two angles have to be congruent, which means I can take the 180 minus the 145, split that number, and come up with both those angles there. Okay. So same here, I got another angle. This is obviously not 45, but in fact, there's two of these. And I often call these like two slices of pizza. It's technically called a sector, but looks kind of like a slice of pizza. And so this is going to be twice as big. So I can do 360 divided by 8 times 2. Or I can think of it as 1/4 of the circle. I can do 360 times 1/4. It's going to give me the same number. That's 90. And once again, if I create a line here, so 180 minus 90 is going to give me 90 to split between those. Both those will be 45. I didn't do that one because I don't know how to split 135 in my head really quickly. And same thing here. I've got a much larger one here. Oops, that's terrible. Let's try to make that a little neater. Okay, there's your triangle. So once again, this is basically kind of I got like 3 slices of pizza there. So this is going to be my 45 times 3. So that's 135, which is a little hard to read there. But then this angle here and this angle here are going to be my 180 minus 135, because that's how much the whole triangle has to add up to. So that gives me 45 left over. And when I split that, that angle will be 22.5. Okay, so it's easy enough to find both the central angles, and if I turn those central angles into triangles, they're isosceles triangles, it's easy enough to find those two remaining parts. Similarly, if I wanted to, I could, I'm just going to draw this in general. So this is not related to the 9-point circle. It's just a angle in there. I might give you something, I might tell you, hey, this over here is 40 degrees. How big's that central angle? In which case, you'd have to, well, I know it's isosceles, so that's got to be 40, that's 80, so down here, that's 100. So that would be a good quiz question. Okay. Another example is if we have a 6-point circle. Okay, 6-point circle here. This angle here is 1/6 of 360, so we know that central angle has got to be 60. Once again, this is a central angle here. This angle over here, one that's, I'm going to do that in a different color actually. That angle over there is what's called an inscribed angle. And I'm doing it this reason. So I've got an angle, connects there, and then this line, which goes to the diameter, goes there. Once again, radius from the center to the edge, diameter from side to side through the center, and this over here is called a chord. Okay, it connects 2 points. So once again, we got a diameter, little review, and radius. Not really what I intended, but as long as I'm doing it. Okay, this over here, this angle over here, this right here is called an inscribed angle. And anything that's inscribed means it's kind of one of the vertices is on the circle. Okay, there is a relationship there. It's not 60. I can look at it. I can see it's clearly smaller than 60 because that mouth got narrower. This arc out here, so once again, this is called an arc when we do it along the edge. That arc out there is the same measure as a central angle. That arc is 60 degrees, okay? Just to be clear, central angle and the arc, what's called the intercepted arc, is the same angle. This is smaller. Now, can we figure out what it is? Well, we kind of can, at least in this picture, because, I can see, that's 2 of those. This is 120. This is an isosceles triangle. So 180 minus 120 is 60. I got 30 to split between those two. Oh, look, that's 30. It is half of that 60, half of that 60. And that will always be the case. If I change that to something else, maybe with a 90 here, that over there would end up being half. This is one example. I'm doing it with specific numbers you can see. We're going to do a general case in a minute, but I want you to see it works with specific numbers. That, oh yeah, in this case, that intercepted arc, inscribed angle, is definitely half of this intercepted arc over here. So I'm going to give you a same example, but a different place. Okay, so once again, we know for sure this central angle is 60, which means this intercepted arc is 60. Now, this is kind of anywhere. This could be anywhere. These numbers could be anything. They're obviously kind of large, maybe in the hundreds. So I'm going to make one up, okay? I'm going to say this is 130 degrees, okay? Okay, now I know what this one is. If this is 130 and this is 60, well, that's 190, and we know everything around the center there has to add up to 360. So that's make sure I do this right, 190. So another 170. That's right. I think that's right. 170 would get me up to 360. Okay. So once again, I made that up, but this works. Now that I know these, what I'm actually trying to show is like, well, is this intercepted arc over here, which let me change colors again. If I move where that is, because in my previous example, I had it along a diameter here. If I move where that is, does this thing still come out as 60? And well, let's see. Okay. If this here is 130, there's 50 left over. So that's got to be 25, as well as that's got to be 25. Okay. And let me change colors again. This one over here, if that's 170, that means this has to be 5 degrees, and this has to be 5 degrees. And so look at that. Those two together, those adjacent angles, add up to 30 degrees. So once again, it is half of the intercepted arc. And so once again, the kind of question that you might get on this, there's two kinds. I can give you something that looks like this, and it doesn't matter where these are. I can say, okay, I've got a inscribed angle here, and it's 20 degrees. How big is this intercepted arc? And the answer is, oh, it's got to be 40. It's got to be twice, because that relationship always exists. And there's a way to prove it. Similarly, I could give you an arc. I can say, hey, this arc right here is, let me pick out something that's reasonable. Let's say it's 50 degrees. I'll tell you that's 50 degrees. This angle over here has to be what? That's right, 25, because it's got to be half. No matter where that dot is on that, will always be that way. Now, we proved it with kind of two specific cases and just using 60. I could do a bunch of others using numbers, but there's a way to do this kind of generically, which I'm going to leave you with. Okay? So ignore where I've connected them to here. This is some number. It's some central angle, which means I'm going to call it x. That means this angle right here has to be 180 minus x divided by 2. Has to be. That one has to be the same size. I can figure those out. I don't know if I need to figure those out, but I can figure those out. I'm going to make up some number here. I'm going to call it z. Okay, just like I made up the 130 here. Okay, if that's z, this one right here has to be 180 minus z divided by 2. In the same way, that's the way I got the 25 there. I'm just doing it generically with algebra. And then finally, the same thing here. This one has to be y, although really, I don't want to get too many variables in there. So instead of y, this is really the same thing I did up here. I added these things up. I subtracted from 360. So this right here, what I'm calling y, is actually, I think you can see that. I'll make it bigger. 360 minus the x plus the z. That has to be whatever's left over. And then whatever that number is, if I take it, I subtract it from 180 and divide it by 2, that whole mess right there ends up being that corner. Now, I can actually solve these two equations to show that, hey, this thing is always going to end up being these two things added together are always going to end up being 1/2 of x. So if this is x, that arc is x, and this is 1/2 of x. I'm not going to go into that proof, but it can be done, and I'm going to leave that challenge with you. Ciao.